Welcome to a session on floating and submerged bodies in water. So we'll do some numericals under the topic floating and submerged bodies. So as part of the theory, we have seen the center of buoyancy. It is a point through which the force of buoyancy, designated as PB, is acting. And as we know, center of gravity is a point through which the weight of the body, whether it is floating or submerged, is acting. And also we have seen the stability conditions for floating as well as submerged bodies. For submerged bodies, we know that the relative position of center of gravity and the center of buoyancy determines the condition of stability. For floating bodies, it is the metacentre that determines whether a floating body is stable or not. In a submerged body, that center of gravity should be below the center of buoyancy for that submerged body to be in stable condition or in stable equilibrium condition. Whereas as far as a floating body is concerned, that metacentre should be above the center of gravity. That is, metacentre is designated as M and the center of gravity is designated as G. So Gm should be positive. And also we have seen Archimedes principle, that is, as you know, it is the weight of the body, whether it is floating or submerged, in air. That weight of the body in air is equal to the weight of the water displaced by the body. So with this knowledge background, we will attempt some numerical problems belonging to the section floating as well as submerged bodies in water. So first problem is related to a floating body. We need to find out the metacentric height of the floating body. So we have seen and we have derived an equation for the estimation of metacentric height of a floating body. The question is like this: a solid cylinder of diameter 5 meter and height 4 meters. Find the metacentric height of the cylinder when it is floating in water with its axis vertical. The specific gravity of the cylinder is given as 0.6. So you have got a solid cylinder. So height is given 4 meters. So it is floating in water. Okay. So we don't know what is the height of that floating body in water. That we have to find out. And also we need to find out the metacentric height. So we know the equation for the metacentric height. So first of all, we will sketch the arrangement. So let this be the floating body, and it is floating in water. Let height of the body is designated as small h equal to 4 meters. Okay, then h1 refers to, it is a representation of the depth of the body in water. That is depth of immersion. H1 is depth of immersion, and G is the geometric center of the body, that is the center of gravity, which is at a distance 2 meters from the bottom surface, because the height is 4 meters. So G will be at 2 meters from the bottom, 4 by 2. And B is the center of buoyancy, the point through which the buoyant force acts. And we know that the center of buoyancy B is nothing but the center of gravity of the immersed portion of the body. That is a center of gravity of the immersed portion of the body. So you can locate the point B if you know the depth of immersion. And how to find out the depth of immersion? And we will try to do this problem. So the given data, the diameter of the body is given as 5 meters. The height of the body is given as 4 meters. So you can find out it is a cylinder. So volume of the body you can find out. It is pi by 4 d square h. That is d and h you have to substitute in meters. You will get V, that is the volume of the body, as 78.5 meter cube. Okay. And specific gravity of the body is given as 0.6. So as we know that the depth of immersion is always the product of specific gravity and height of the body. This equation we have derived while explaining the theory. So this equation we have derived on the basis of the Archimedes principle, that weight of the body in air equal to the weight of the liquid displaced by the body. So with that particular, from that first principle, we have derived the equation h1 equal to s into h, that is depth of immersion is equal to the product of specific gravity into the height of the body. So this is h1. So what is h1? 0.6 into 4, that will give you 2.4. So the depth of immersion is 2.4. So what about the position of B, the center of buoyancy? Center of buoyancy will be the center of gravity of the immersed part. So B will be at a distance of 1.2 meters, that is 2.4 divided by 2, that is 1.2 meters from the bottom surface. Okay. Volume of the water displaced by the body, that is represented as V immersion, that is equal to volume of the body in water. So an equal volume of the body in water will be the volume of water displaced, that we know. That is, what is the volume of the body in water? It is pi by 4 d square into h1. So if you substitute d and h1, you will get 47.1 meter cube. Okay. And for the estimation of metacentric height, the equation is, we know the equation for the metacentric height. So Bm, that is the distance between the center of buoyancy and metacentre, that is given as Ig by V immersion. Before that, we need to find out Ig. So what is Ig? It is a moment of inertia of the body through its central axis through the center of gravity. It is a cylindrical body, so you have to study the equation for estimating the moment of inertia of any body through its central axis. Since it is a cylindrical body, Ig equal to pi by 64 into d raised to 4, that is 30.66 meter raised to 4. Okay. Then Bg, that is a distance between center of gravity and this vertical distance, center of gravity and center of buoyancy. So that is, as per this figure, it is 2 minus 1.2, that is 0.8. So Bm, that is a distance between center of buoyancy B and metacentre of the floating body. It is Ig by V immersion. This formula also we have derived. Ig is 30.66, V immersion is 47.11. So you will get Ig by V immersion as 0.65. So what is metacentric height? Metacentric height will be Bm minus Bg. Okay, Bm minus Bg, that is the metacentric height. So 0.65 minus 0.8, that is minus 0.15, that is negative, that is body is unstable. So for doing such problems, we need to find out the metacentric height. Metacentric height definition you need to know, that is Bm minus Bg. So what is Bm? Distance between B and M, center of buoyancy and metacentre. And Bg, what is that? It is a distance between center of buoyancy B and center of gravity G. Okay. So if metacentric height is negative, we say that the body is unstable. Okay. Now we move on to the next problem in this section. The question is, find the density of a metallic body which floats at the interface. Again, this is a floating body question at the interface of mercury of specific gravity 13.6 and water, such that 40% of its volume is submerged in mercury and the rest in water. Okay. So here you have got two fluids, one is mercury, other one is water, and this metallic body is resting, or it is floating at the interface of mercury and water. And what is the condition? 40% of its volume. If the volume of that body is V, 0.4 V is in mercury and the remaining 0.6 V, that is 40%, and the remaining is 60%, that is 0.6 V is in water. Okay. So how to do the problem? We need to find out the, first of all we shall have to sketch this, even though a sketch of this particular problem is not required. If you want, you can do it. How to do this problem? This is as per Archimedes principle. You see this? Weight of the body in air equal to weight of the fluid displaced by the body. Here you have two fluids. Okay. So this Archimedes principle, we know weight of the body in air is equal to weight of the fluid displaced. Here you have two fluids. So in one fluid, the volume is 0.4 V of the body, In the other fluid, the volume is 0.6 V of the body. So what is the weight of the body in air? It is equal to, weight is mass into acceleration due to gravity, m into g. So what is m? M is density into volume. So density of the body into volume of the body will give you mass, multiplied with g will give you weight of the body. What is density of the body? Okay, that we can find out. Then weight of the fluids displaced by the body. We are going to substitute in this equation. Weight of the fluids means weight of mercury plus this is weight of water displaced. Okay, what is weight of water displaced? How to get it? It is m into g of water. M into g of water means density into volume of water displaced into g. So density of water into, this is g. What is the volume of water displaced when that body is immersed or floating? Because 60% is water. So if V is the volume of the body, the volume of water displaced will be 0.6 into V. Okay. Similarly, volume of the mercury displaced will be 0.4 into V, because when a body is immersed or floating, or it is immersed in a water, the equal amount of volume will be displaced. When a body is immersed or submerged in a liquid, volume of the water or that liquid which is equal to volume of the body will be displaced. Okay, so in water the displaced volume is 0.6 V, whereas in mercury the displaced volume is 0.4 V. So the respective weights will be rho of water into 0.6 V into G for water, and for mercury it is 0.4 V into G into density of mercury. So what is as per this equation? You can substitute as per this equation, that is weight of the body in air, that is rho body Vg equal to weight of water displaced plus weight of mercury displaced. So what is density of mercury? Density of mercury is 13.6 into density of water, because the specific gravity is given as 13.6. Okay, so you can simplify this equation, because V cancels off from both sides of the equality symbol, G also cancels off. Okay, then the equation you are getting is, if you are dividing throughout by Vg, okay, you will get rho of body equal to rho of water into 0.6. Here it comes 13.6 into 0.4 into rho of water. So rho of water we know it is 1000 kilogram per meter cube. So if we substitute the value of density of water 1000 kilogram per meter cube, you get the density of the body as 6040 kilogram per meter cube. Okay, so in this problem we have used only the Archimedes principle. So you should understand, because always remember it is weight of the body not in water but in air, that is equal to the total weight of the fluids displaced. If we have two fluids, we have to add together the respective weights displaced by each fluid. Okay, so in this way you can find out the density of the body. We'll move on to another problem. Okay, the problem is like this: a wooden cylinder of specific gravity 0.6, okay, of circular cross section, okay, is required to float in oil of specific gravity 0.8. okay, so the specific gravity of cylinder is 0.6, but as of that of oil is 0.8. okay, find the length to diameter ratio, that is h by d, length to diameter ratio of the cylinder, that means height to diameter, h by d, length means height here, if the cylinder is to float in water with its longitudinal axis vertical. A wooden cylinder of specific gravity 0.6, which is of circular cross section, is required to float in oil of specific gravity 0.8. okay, we need to find out h by d ratio of the cylinder, or h to d ratio of the cylinder, if the cylinder is to be in equilibrium with its longitudinal axis vertical, that h is in vertical, h is the vertical height. So in order to have that longitudinal axis vertical and to keep that cylinder in equilibrium, the condition for that floating body is, as we know, the metacentric height should be positive, that is metacentric height should be greater than or equal to 0. So we'll try to sketch this figure, this arrangement. This is the cylindrical body, wooden cylinder, circular cross section. Okay, and height is h, the diameter is d. Okay, so what about g? G is the center of gravity of that cylinder, and it is at a distance of h by 2 from the bottom, because h is the total height of the cylinder. Okay, so what is b? B is the center of buoyancy while it is floating in oil. Center of buoyancy means it is a, as I already told, it is a center of gravity of the immersed portion of that body in the oil. So let the immersed portion is h1. So h1 is the depth of immersion. So what about OB? O is the bottommost point. OB will be h1 by 2, because it is the center of gravity of the immersed portion. So h1 by 2. So OG is h by 2 and OB is h1 by 2. So what about BG? Let us see. And M is, suppose it is the position of metacentre. G is the center of gravity of the body. B is the center of buoyancy of the body in water. It is not water, it is oil here. Okay, so there is a small correction. It is not water, it is oil. Oil of specific gravity 0.8, and it is wooden cylinder of specific gravity 0.6. So for the cylinder in equilibrium, the condition is metacentric height should be positive. So with reference to the figure, you can find out BG. As I already told, it is h by 2. BG, this distance BG is OG minus OB, that is h by 2 minus h1 by 2, that is 1 by 2 into h minus h1. For the equilibrium, GM should be positive. What is GM? Vertical distance between center of gravity and metacentre M. So GM means what? GM means BM minus BG as per the figure. Okay, so GM is positive, should be positive. That means BM minus BG should be positive, or BM should be greater than or equal to BG. That is equation number 1. So what is BM? BM, we have the formula Ig divided by volume of the immersed portion, or volume of the water, sorry, volume of the oil displaced. So what is Ig for this cylindrical figure or cylindrical object? Ig will be pi by 64 into d raised to 4. And what is the volume of oil displaced? It will be pi by 4 d square into h1, because h1 is the depth of immersion of the body in oil. So you get pi by 64 d raised to 4 divided by pi by 4 d square h1 will give you d square by 4h1, that is Bm. So what is Bg? Bg already we have calculated 1 by 2 into h minus h1. Okay, so what is as per the equation 1, what is equation 1? Bm should be greater than Bg. So d square by 4h1 should be greater than 1 by 2 into h minus h1. That is written over here. D square by 4h1 should be greater than or equal to 1 by 2 into h minus h1. That is equation number 2. Okay, we are going to find out the minimum value of h by d. So you take the equality symbol. It should be greater than or equal to. So if you take the equality symbol, you can solve for h1. Okay, so but if we know that the depth of immersion is equal to this. So what is depth of immersion? That also we have derived. So remember, depth of immersion of any body in any liquid, it is equal to specific gravity of the body multiplied by height of the body. Okay, so what is the specific gravity here? It is 0.6 into height of the body, that is h. So if you substitute h1 equal to 0.6h in this equation 2, you get 1 by 2 into h minus 0.6h. That is 1 by 2 into h minus 0.6h. And here also you substitute for h1, you can substitute 0.6h. So if we take the equality symbol and solve, because the unknown quantities are, one is h, other one is d. Okay, and as per the problem, we need to find out the ratio of h to d, or h by d. So if you solve it, you can easily get h by d, because 1 by 2 into h minus 0.6h, this will be 0.4 h by 2, that is 0.2h, and d is here. So d square you will get So h by d will be square root of 1 by 0.48 or 1 by square root of 0.48, that is 1.44. So in this problem also we have found out the metacentric height, and it should be positive, that is a condition applied. For that condition, with the longitudinal axis vertical, the h to d ratio or h by d should be 1.44 minimum value. And you have a task. This problem is very similar to the problems we have just discussed. The last problem we had discussed. What is that? A solid cone. Here the geometry is different. Instead of a wooden cylinder or rectangular cylinder, we have taken a solid cone. So you can find out that volume appropriately, and also you need to find out the position of the center of gravity, because for a triangle or a triangle shape, the position of the center of gravity is 1/3 of the height from the base of that particular cone, or it is 2/3 of the height from the apex. That you should know, and you should know the equation for finding out the moment of inertia Ig of the solid cone. Floats in water with its apex downward. So it is like this, floating in water. Base is at the top position. Determine the least angle of apex. So this angle, suppose it is theta, of the cone for equilibrium. So here also you can find out the metacentric height and make the condition metacentric height should be greater than or equal to 0 and equate to 0, metacentric height equal to 0, and you can find out that theta, that is a least angle of apex. So this concludes the numerical problems belonging to the section buoyancy and flotation, or floating or submerged bodies in liquids. Thank you.